Okay, I just click the record button. So I think today's topic, in this video, we just want to discuss one topic, which is the variance strain. So there are a couple of different names for this variance strain. Some call it volatility drag, some call it volatility tax, some call it variance strain, but they are all the same things. So just to look at the slides that I'm sharing here, right? This is just the definitions of the variance strain. It is defined as the difference between geometric return and arithmetic return. So to keep it simple, arithmetic returns, right? Basically, it's just like, say, for example, we have 5 different samples. You just sum it up 5 and then divided by 5. So that's the plain average. That's the arithmetic return. But for geometric return, this is more like a product, right? So for example, we have 5 years of return. Basically, you compound it over 5 years. And if you want to take the average, you just power it to the 1/5, right? So this is different calculations, geometric and arithmetic. But I think we just want to get into some technical details between like why is it so that when we calculate the returns on geometric basis, right? How come there's this so-called drain? It's as if like the returns just disappear away from the calculations. So if we look at the formula, right, this is the estimations. Basically, you just take the variance divided by 2, then you can get the difference between the arithmetic and geometric. So I think up until this point, it sounds like there's still like quite blur, like okay, why is it all this about, right? So I think the best way to understand this, right, is just to look at examples. So using like Excel or Google Sheets. So I think this is the best way to explain, right? So start from the simple one first. We start from arithmetic returns. Okay, let me just enlarge it slightly. So for arithmetic returns, right, I just give a hypothetical scenarios. Say, for example, like we go to casino and do some gambling, right? So there's this gambling outcome. So it's like you buy big or small, for example. So each of them is like 50% probability. And then the outcome, right, let's say there's 50% probability that you get 70% return. So 70%. Then the other one is that you will lose 50%. Okay, so this is the outcome and this is the probability. So if we just care about arithmetic returns, right, we want to know like, okay, if we repeat playing this game again and again, right, what's the expected value that we can get, right? So the expected value is basically just the sum product of the outcome with the probability. Because when I win, right, let's say half of the time when I win, I get 70%, but half of the time when I lose, right, I lose 50%, right? So the expected, right, is like 10%. So for example, now I offer you, right, I say, why not, like I'm the casino, you can bet this, you can bet like 1,000 times, doesn't matter. Would you want to take this bet or not? So I think the simple answer to this question is you will want to bet this because there's 50-50%, right, that you will win and you will lose. But when you win larger amount compared to the amount that you lose when you lost the bet, right? So if we put this under simulations, right? So for example, like the type of bet is that we reset every time, okay? So you do this bet, okay? Let's look at the outcome and then whether you win or lose, right? Then we repeat again and repeat again and keep on repeating. So you either win or lose, nothing get compounded over time. So this is the time period, basically, if we go from left to right, right? So we have 30 years of, we play, every year we play once. And the simulations, this one is just like, okay, there are different outcomes. We try to simulate the situations, right? The scenarios. So you see here, basically these are just some formula. I use the random formula here. So let's say if it is less than half, then the outcome is that you will have a 70% gain. So the other half is that if it is less than 50%, right, then you will have a 50% loss. So this is the outcome. It will look like this. So it's either like 70% or minus 50 or positive 70%, minus 50%. So if we just repeat this across, let's say 30 years, right, and then we take the average, right? So this is my average here. Basically, this is just an arithmetic average, right? Because we just repeat the outcome every times, okay? So, and then this is just 30 years across one simulation, if I repeat the simulation over 1,000 simulations, right, and I take an average of all this outcome, right, you see here, this is average of all the average here until 1,000 simulations, right? So what we get is 9.7%. So this is, although this is like simulations, right? You see, I can refresh. Basically, I just click something here, right? You recalculate one. You see, it moves, right? You recalculate. So the outcome here, this will be very close to the expected value that we are going to get here, because basically what happened is that we have 1,000 simulations times 30 years. We have 3,000 data points. Out of that 3,000 data points, around half of them will be positive 70%. The other half is negative 50%, right? So you take an average, right? It will be about 10%. You won't run too far away because we have enough data points, right? So this is arithmetic returns. Basically, if we just repeat the same thing as if they are independent to each other, right? This is how it looks, right? Very simple for arithmetic. Okay, so next one is we want to ask like, okay, what is going to happen if it is not arithmetic? So what kind of situations that we will use the geometric return instead of arithmetic return, right? So this is the second one that basically we want to look at. To put it simple is that, you see the outcome is still the same. There's 30 years return here, and then also I have 1,000 simulations, right? But when it comes to investment return, right, we don't reset it every year, right? So say for example, I start my portfolio with $10,000. So if I get 10% return, my 100,000 become 110,000. Then that one become a new base, right? Then another year I could lose 10% or 5%, or I could gain whatever amount, right? So it will be like a multiplicative effect, meaning that by end of 30 years, the portfolio size depends on the compounding value across these 30 years. And the compoundings, right, is like a geometric kind of calculations or product or multiplicative. So if you have a 10% return, basically it is like multiply 1.1. If you have 20% loss, you multiply by 0.8. So it is multiplicative effect rather than just arithmetic, like every time you reset, right? This one, it doesn't reset. So to put it simple, let's say if you gain 50%, right, and you lose 50%, right, as if you are like, okay, gain 50, lose 50, by right average out is 0%, but actually you will result at 25% loss. This is because of the multiplicative or because of the compoundings. But in this, back to this same example, I take the gain is 70%, but you lose 50%, right? So if you get 70%, basically you multiply 1.7. If you lose 50%, you actually multiply it by 0.5 to get the portfolio value by the end of that year. So on the first part here, this is from column F to column AI, right? This is just the return. It's exactly the same as the arithmetic. But in order for me to calculate the end value, right? So I need to have these calculations that is essentially to calculate the portfolio value, right? Here at time 0, I started out with 1. So this is time. So I started with 1. Then depending on the value here, right, you can see that the calculation is basically just take the value at the previous period, multiply 1 plus the return, the first year return here. And of course, if I'm looking at the second year, right, second year is the year before that, multiply it by 1 plus the second year return. So this is basically try to project out what is the portfolio value by the end of first year, second year, third year, and so on and so forth. And then I repeat the same thing for 1,000 simulations. And then by the end of it, right, I just want to calculate that, okay, under the first simulations, right, what is my return? And this is the geometric return, right? Meaning that I take the end value at 30 years, right? This is the end value to the power of 1 divided by 30. So meaning we analyze it to see what will be the return throughout this 30 years period, and then minus 1 to get the returns. So basically, this is just the geometric return calculations. And then if you take this entire 1,000 simulations, right, and similarly, I calculate the average of this 1,000 simulations, right, you will notice that I'm not getting back the 10%, even though if we just look at this probability, right, if I gain, I get 70%. If I lose 50%. The expected is still the same, right? It's still the same kind of calculation as the arithmetic return. I should get a positive 10%, but why is it so that I get something that is much lower? You see, I can refresh the spreadsheet, right? I just put in one here, then it will refresh. See the spreadsheet move, right? After refresh, I still get something that is like negative, although my expected return is positive. So here, what I try to explain here is that because when you lose 50% and then you gain 70%, right? So let's say 1.7 multiplied by 0.5, you get something like 0.85. So every two times, right, you actually lose 15%. So on average, every one simulation, you actually every time step you actually lose about 7.5%. So this is because of the geometric calculations. So if you want to estimate like what should this return be, right? Because now in this spreadsheet we are talking about geometric calculations. It's no longer arithmetic returns, right? Basically, you can just look at the drag, right? So you remember the drag that we just discussed about. If you want to estimate the drag, right, you just take the variance and then divide it by 2, right? So here we can calculate the variance based on this probability distribution, and then basically you just take the variance divided by 2. This is 18%, right? What it means is that although the expected value is 10%, but because the volatility of this game, right, this 50% chance of 70% or minus 50%, this one variance is very big. This is bigger than typical equity volatility, right? And if you take this and then you just calculate the drag, right, this is 18%. You take 10 minus 18, you get something like close to, let's say, negative 8%. So what happened here is that although the expected value is positive, but because the volatility is too big and the variance drag is very, very big, after minus out, right, the expected value, after minus out the drag, right, you get back something like a negative returns. So all in all, just want to illustrate that under geometric returns, as long as you have a outcome that is highly volatile, so that will actually exert a downward drag to your returns. Just because, for example, I think I'm sure you have heard of this, right? Let's say if you lose 10%, you need to gain like 11.1% in order to get back to zero, get break even, right? So if you lose 20%, so your money is left with from 100 drop to 80, right? You need 25% to get back to 100. So basically, this is the effect. So I think for those who are interested with the mathematics, right, you can study those like Jensen inequality to understand why is it so. But I mean, for layman people like us, right, if you just do some Excel modeling, and then you can basically just see the effect. Like this one, you can just do different simulations. After they refresh, and then you look at these numbers, right, it will always prove you that the variance drag, right, is real stuff. So if you have a volatility that is a portfolio with very high volatile outcome, right, or volatile returns, right, you will experience the drag over time. That's why for those who invested in, let's say like TQQQ, right, the 3X Nasdaq 100 ETF, right, because the volatility of the Nasdaq 100 is already very high, you multiply it by 3, the variance drag it will become very serious. So this is something to take into account, into considerations. So I think this is just some illustration on how this thing works. I'll just stop here, and we can stop the recording here, or we can just have some Q&A just to see if you have any more questions.
How do you get the variance?
You mean which one? The variance here? This calculation?
6% calculation is just a difference between arithmetic means and...
No, this variance, right, is just the this variance is just the statistical formula, which is the expected of x squared plus minus the expected value of x square.
Uh-huh.
You know,
Okay.
so I type it here for you. So it's like x square, something like this, minus expected value of x, then square, something like this. So this is the formula of variance. Yeah, but for this is an extreme example just to show, make it big. I mean, you see, this is the variance, right? So if I calculate the volatility, right, it is around, let's say, can I see this? This is 60%. So this is even double of a normal equity volatility, right? Equity volatility is about, I think for world economy or S&P 500, I guess it should be around 20%. For emerging market, it could be as high as close to 30%. But this scenario, this is like a casino distribution, right? So 60%. That's why you can see the drag very serious. But let's say if we change this one to, let's say 30%, and then this one is minus 10%, right? Then you can see that even though I think they are, yeah, so the expected is still the same, but you see the average now is a lot higher. It's no longer positive here, right? Because the drag, right, now this distribution is a lot more, variance is, or the volatility is a lot smaller compared to the first one, right? So if we change this, you can see that the expected value is still the same, it's still 10%, but the average of 1,000 simulation now I get something like 8.4%, right? And similarly here, I can calculate the variance is 4%, and then the drag should be about 2%, right? You take 10 minus 2, you get something like 8%. So this is quite close already, right? Yeah.
Okay.
Yeah. So I think the key point here is that because we are not comparing, like the discussion last night, we are not comparing equity versus fixed income. This is got nothing to do with asset class. This is just like hypothetically speaking, because we are talking about mathematics, right? Hypothetically speaking, we have two portfolio with the same expected value, meaning this is the drift, right? This is the expected value, or the, how to say, the expected return. And this is the volatility, right? So the first one and second one, their expected value is still the same. It's just that previous one, because the volatility is very high, so every time you have a loss 50%, you need 200% to break even, right? So that one, it causes a downward pressure or a downward drag to the overall return when you compound your portfolio value. That's why it's very hard to compound if you have a very volatile portfolio. So here we reduce the volatility, even though expected value is still exactly the same, right? Now you can see that, I mean, towards the end of the value, right? If you run 1,000 simulations, the average is a lot higher, right?
Yeah.
So this is just the maths, just the mathematics itself. If we bring in the comparison between equity and fixed income, then it will be very different, because the expected value itself, right, is very different already. Because for equity, you might want to include in the equity risk premium into it. And the equity risk premium is easily, let's say, 4 or 5%, right? So the drag itself will be of a less impact as compared to that 4% drift, upward drift, when compared against a bond portfolio. So that's why it's slightly different. So
Yeah.
yesterday discussion, it's a bit it's a bit like all mixed together. At first, we talk about all this volatility drag. Then we give some hypothetical example of bond versus equity. And then in the end, suddenly bond portfolio become higher return compared to equity because of the lower drag, right? Which isn't the case, right? Because now you have two different portfolio with different expected value. This is the expected value, and then different drag, right? So you need to separate out the two effects.
Okay. I think so far I can understand the math behind it. I think it's more to do with the expected value. It's actually the formula there is actually applying on each like each year or each simulation each year.
Here.
Yeah. I mean, it's a 10% is every time is like throwing a dice. Every time, half of the time you get 30% gain.
Yes.
The other half of the time you get you lost 10%.
Correct.
So is the expected value is the expected value of each time.
Yes, correct.
Whereas when you look at if it's really a throwing of dice, then it will be a arithmetic case where your after 30 years there isn't any compounding because each time it's reset lah. So it's really throwing a dice, case of throwing a dice, and the arithmetic mean is the one that gives you the overall the return over 30 years. Whereas in the case of investment, in this case, like you are investing and there's a compounding effect there because your capital keep changing.
Yes.
At one point it go up 30%, another point it drop 10%. So it go ups and down, and that's I can understand that that actually would be the volatility because But then as what you have shown in that case, after 30 years, the returns has to be based on the geometric means, not arithmetic, because it is a multiplicative situation.
Yes.
So in other words, here what happened is that the expected value is based on one time, whereas this is a one-time thing, and then where the variance is calculated based on. Okay, so the variance is the statistical formula to calculate if you do this over, let's say 30 times in this case, what the expected, the range of expected value could potentially be lah. That means it can vary like in this case it's 4%, maybe plus minus 4% from the 10% expected value. Is that what it means lah? Is that what it means?
Yeah, I think okay, I later I'll come back to the difference between arithmetic and geometric, but what you try to explain here is that when we say the variance, right, it has nothing to do with 30 years. The variance, right, is just a measure for the dispersion of the outcome. Because right now, let's say take this as an example, right? My outcome, I know that it's either positive 30 or negative 10%, right? This is my outcome. How big is the dispersion, right? Depending on the probability and depending on the outcome itself, right? The value of the outcome. So here, if we just say, it doesn't matter whether this is like one simulations or 1,000 simulations, and doesn't matter this time period is like one time period of 1 year or 30 years, right? Basically, the game that we are playing here, this is the game, right? And from this alone, we already know that the variance, right, is 4%. This is mathematics, right? It's just based on whatever that coming out from the formula here. So this is the outcome itself. If I put this one become like just now in the beginning, if I put this one as positive 70 and minus 50% here, right? So I get this dispersion is even bigger, right? Because now you don't have a middle returns. You either get very high return or very low returns. So dispersion is higher. Your variance is also become much bigger, right? And it has nothing to do with how many years. But now come back to the questions on like you say we are calculating the average of 30 years, and if we see this as like how our portfolio is running, right? Of course, if we just compounding, of course we should calculate the average based on the geometric returns, because the geometric returns is the real returns. But how can I structure this? Like just now in the beginning, I talked about like arithmetic returns, and then we just reset every time, right? You can actually change the game such that the outcome, it becomes more like an arithmetic kind of returns, right? Say, for example, now you bring $100 to the casino, right? You place your bet, and then regardless of the outcome, right? Say you put 100 in there, okay? So you either lose $50 or you gain $70, right? So this is the game that you're playing. So every time after you place that bet, regardless of whether you win or you lose, right? You say for example, you win. You put 100, now you get 70, okay? Then you have to take the $70 put back into your pocket and restart again with $100, okay? So you just play that again. And if you win, you just repeat that. You win, you take back 70, and then you just restart at 100 again. Basically, this is how you work. But if you lose money, say you lose $50, right? You put 100, you lose 50. Then you have to take money out from your pocket and top up that $50 and restart it again at 100. So if you say, this is how I'm going to play it, right? You can always say, I lose money, I top up, I lose money, I top up. If I win, I take back $70. You can actually come up with this type of arithmetic returns because your outcome will be kind of like positive expected value already. Just because you are able to repeat this again and again, and you know that the outcome, right, you are either 50-50 chance that you will win 70 or lose 50. So you can structure it in such a way that arithmetic return is more applicable to how you play the game. But come back to the geometric one, which is how we manage our portfolio, is that we always have a portfolio, and this portfolio, if we earn money, we don't take back, right? We just compound it along the way, right? And because of this compounding, say for example, like I can have a 10% return for 20 years, and then I only need 1 year of 90%, right? 90% loss, right? Then I kind of like already wipe out my portfolio already. Because why? Because the compounding nature, right? So it's very like we are heavily penalized by an outcome which is very, very big losses type of outcome. So the effect is not symmetry one. The effect is not like arithmetic return. The effect is multiplicative, meaning that if we lose 90%, our portfolio is basically gone. Regardless of we get the 10% for many years, right? Yeah. Or worse, right? I mean, for those who leverage out, let's say 5x leverage, right? You can have 30% return for 30 years, meaning that your return is higher than Warren Buffett, right? Then you only need 1 year of like negative 100% return, then you wipe out, right? So basically, it's not symmetry. So that's where the drain come into the picture. Yeah. So I hope that this one, like if we understand the setting of the game, right, then we know that, okay, why is it so? How come, like, as if like, in order to know how much my portfolio will go up over 30 years, right, to know the expected value is not enough. For example, this game, right, I know that I should be able to get a positive return, right, because the game, the outcome is in favor of myself because I get a higher return when I win than the money that I lose when I lose, right? But just from running this experiment, you can see that most likely if I invest in such a way, right, my return is actually negative. It's proven here, right? You see here, average here. So it's negative one. You can refresh this spreadsheet again, right? If you just refresh, right? Then you come back again, negative 7% become negative 6.8. You see, it's likely that this one will be a negative, but doesn't mean that every time it will be negative, because you look at the simulation, it could be like, negative 18, negative 15. Some situations I get a positive 4, positive 13, positive 17, also possible. But you average out across like the 1,000 simulations, you will notice that actually my return is not going to be a positive one. It's likely that I get a negative return than a positive one just because of this drag. Right? Yeah. Okay, so I will stop the recording here. Just stop the recording for the purpose of upload later. Okay, I'll stop recording. Thanks a lot for whoever who is watching now. All right, stop the recording first.